Welcome back. So we will start our next session because we have a lot of content, so we need to like catch up with the timing. Okay. So since you have no questions, so we'll proceed to the next one. So the next one is about this autonomous navigation. So once we have the map, now we talk about how to use the map to move the robot from point A to point B safely, without collide to anyone, anything, even if you have dynamic obstacle, like someone move around and so on, we can still. So we will show you how to do this. I will explain to you the concept of path planning and so on. And later on, the most exciting part is the map that you generate in simulation and also the program that you write using the simulator. You look at the result in the simulator is going to be ported. Your code is going to run on real robot in real environment, and you can see the comparison. I can tell you it is almost like 90% accurate, or 99%. It's actually very, very accurate. So later you can see, right, the comparison. Right, so let us start because we have a lot of contents to cover. Okay, David, next. Okay, so I will skip this, next. Right, so the second part is our focus. The objective is to let you understand how to make the robot able to navigate from point A to point B autonomously. Right, but before that, I need to explain one very important concept is how the robot do motion planning. Okay, in order for you to understand how the navigation works. Right, you need to understand how the robot do motion planning. Okay, so I'll start the motion planning. Next. Next, okay, right. So I will start with a very brief explanation about this motion planning, this autonomous motion generation concept. So I will take you away from the navigation for the time being. So I'll explain this concept first. So let me remodel or put you in a very simple scenario. For example, in navigation, okay, so we have something, you start look from the top left-hand side. So we have a blue color rectangle, which is represent the obstacle, or you can imagine it is a wall. Then we have the green box, which represent the starting point, and the red box, which is represent the goal point, right? And then maybe not easy to see, is not so, you can see like boxes on the picture itself, right? You can see like it is being discretized. So these actually represent the steps of the robots can take. Okay, we need to discretize, and the box is big, the steps big, just to show you a simple concept. But in real world, this step can be very small. It's in a very tiny frame. Okay, right. So you just try to imagine. I just enlarge everything to explain to you the concept. Okay, right. So how to move from the green box to red box? First, we need to have a path. The robot need to come up with a path in order to move. And this path have to avoid the obstacle and also avoid any potential collision. And also we might want to have a path that is good enough. For example, like you want the shortest path, you want the nearest turning and so on. You want to reduce the cost in terms of moving from point A to point B, right? So in order for all these things, we use algorithm. For example, over here, I use A star algorithm as an example. Okay, it is not necessary to be the exact algorithm being used in the coding or in the program later on, because I need to start with something very simple. So I use A star as an example. So A star is an algorithm that to use the shortest, the path with shortest or lowest cost, shortest path and so on. But the lowest cost not necessarily is the shortest path, because sometimes it's about the other factor. For example, the cost for the travel. Okay, the cost for the travel. For example, you need certain costs like petrol and so on. So we might not always measure with the distance, and sometimes it's the time, because shorter distance doesn't mean that you use shorter times to achieve, because of the traveling might be different. Okay, so A star algorithm is used the shortest to find the shortest, the lowest cost in every step. Okay, so how to use this to generate? Okay, so now another concept come in. So in every steps, we have the next possible option. So you can see like the green box. So the next step, we have 8 options that we can choose. Then if we move to another box, we have another 8. If it don't overlap with the obstacle, then we have another 8 and so on, right? But of course, among the other 8, you have one that is repeat the previous steps, which is something that you don't want. Okay, so how to understand all these concepts, that what is the next step and how you proceed with the next step, and eventually you reach the goal. Okay, so now I use a simple games for you to understand this, what we call the state space and searching problem. Okay, so David, please run the next slide, please. Next slide. Okay, so I'm going to show you a demo of this Hanoi Tower. You might heard about this Hanoi Tower, you might never heard about this Hanoi Tower, but I think it is a very popular game. But it's a very useful things for us to do this kind of, to explain this state space and search problem. And it used by a lot of experiment research in terms of robot learning and so on. Okay, so David, please run the demo. Right, so this is a small program to show you how the Hanoi Tower works. So Hanoi Tower, we have 3 towers. Okay, over here you can see like tower 1, 2, 3. And then we have dish. Over here you call it the dish, which is like the circular dish. And the number can be starting from 3, 4, 5, and increase. You can increase a lot, right? So the objective of this game is to move all the dish on tower 1 to tower 3. Okay, so that is the objective. And the rules is like in every steps, you can only move 1. And every steps that you move, you need to make sure that the smaller dish is always on top of a bigger dish, which means a bigger dish cannot put on top of a smaller one. So that is the only rules. So your challenge is to find out the minimum steps in order to move the whole, all the dish from tower 1 to tower 3. So that is the objective. So over here, actually, this is a mathematical, also it can be solved mathematically. So if you search on the web, Hanoi Tower mathematical equation is already out. Okay, so people already model this in an equation and you can solve it. And with the equation, we understand that in order to move this 3 dish from tower 1 to tower 3, the minimum step is 7. Okay, you cannot do something lower than 7. If you can do something lower, please show me, because that will be a breakthrough. Okay, right. So let's try this. Okay, so we can see like David start to move like 1 step and 2 step. David, can you like please make it a bit slower? Right. Okay, yeah. So the first step is we move the pink one to tower 3. Okay, then we move the second one to tower 2. Then so this is the second step. Then the third step is move the pink one to tower 2. That is the third step. And then the fourth step is move the orange one to tower 3. Then we move the pink one to tower 1. And then you know, like, yeah, the yellow one to tower 3 and the pink one to tower 3, which is 7 steps. So you need 7 moves or 7 steps in order to reach the goal. Okay, so now you understand this. So just in case in any steps you make any mistake, then you will have more steps to go, right? Okay, so let's go back to the slide. So now you understand this. Go back to the slide. So I try to draw out the possible steps that you can see in a tree form. So we start from 3 dish. Then after that, we have 2 options. It's either you move the top pieces, the top piece to the tower 2 or tower 3. So from the top layer to the second layer, you have 2 options. Then if you choose the one on the right-hand side, then you have another few options and go down and go down and go down, and eventually you reach your goal. So every steps, okay, we can call it is a stage, okay, a state. And then all these state, we will have a state space. So you have a space with a lot of states, possible states, right? Then search problem is how we want to find a path from the top layer until the bottom layer. So this path is our search problem, right? So over here we have a few key definition. For example, the search tree, which is the search tree, and in every state it is called a node, and then the link between them is called link, and we have the start state and the goal state. That is what you want, right? So next slide. Right, so I tried to redraw just now the search tree into something that might look familiar to you. Okay, the search tree on the right-hand side maybe is similar to the one previously. This is just to tell you about the end layer, the child, and then so on, this concept. But if you look at the left-hand side, can you see it resembles something? It resembles, for example, your public transport map, right? Your public transport map, whether it's a bus or a MRT or so on. Okay, a train map and so on. It looks very similar. Like you have many stations, and each of these stations link to each other, right? And then you can select like which path, like you need to pass through which station in order to reach certain goal, right? And each of these link between the station, you might have different time because the distance between two stations might be different from different stations. And then the fees, for example, the bus fees, the train fees might be different, the time travel might be different. So the search problem is how we can find a path from point A to point B. So it's very similar. Like nowadays, you can use apps to do this. So what the app's doing is basically this search problem. Okay, so now you have an idea how this thing is applied in real world. Okay, so next. Right, so in order to solve this search problem, actually this application can apply to many other things, including, for example, how to solve the chess. Okay, I'm talking about the classical chess. It's not the recent goal. The goal is a bit different, okay, because of the modeling, and this search problem is a bit different, right? But the classical one, the chess, is very similar like this search problem. So in every step, you have a lot of possibility, and in all the possibility, you have many more possibility. Then you have a very big search space for you to search the path in order for you to reach. And also in chess, you are taking turns. So two person is doing the decision. So you need to predict what the opponent is doing. But over here, for example, the train and so on, one person is doing the decision. So the robot can decide everything by themselves, and you can control more things. So this search problem, we have a lot of algorithm, and I believe in computer science, you can find a lot of ways to do this, because the application is a lot in computer science and they have a lot of ways. But over here, I just want to use the simplest one to explain you the concept. So over here, we have the breadth and the depth first search. So over here, we talk about the deep and also the width of the search tree in order to get the path that we want. Right, next slide. Okay, so what are these two search algorithms? So the first one, the idea is we try to list out all the possible options in every step. So for example, you look at the right hand side, we from A, then we look at what is the possible things for A. The next step is B and C. Then in B, we come up with all the possibility, and then we go back to the peer, which is a C, and we see what is the possible. So it try to list out all the possibility in each layer. Okay, so this search problem is like for this search, because we are using a computing power to do the search, so it is very important for us to understand the order of the time and also the space, because this is the cost, the computing cost that acquired for this algorithm, because we compare the algorithm based on the computing cost. Right, so this is one way. So let's compare to the next one. Next slide. So if we compare to the next algorithm, which is we focus more on the depth, which means we try a different mindset. We don't list down all the possible option in every layer, but we try to select one way and go deep down. Okay, so example from A, then we got BC. Then in BC, we start to select B and go down. Okay, so we put aside C, which means we try to focus on certain, because maybe like B is actually lower cost than C, so we continue with B. Then B, you go down to DE, which is D is lower cost than E, so you choose D and go down some more. So you have your certain criteria, then we go down some more. And over here, we try to go until we stop somewhere, we start somewhere. H might be not the goal, but that is the dead end. You cannot go anymore. So if you have that problem, then you go back one step and do again, right? Then you go back another 2 step, 3 step, until you cannot go anymore, then you go to the next branch. This is different from the previous one in terms of like it focus to reach deeper compared to the other one, which is lists down all the horizontal pillar. Okay, then you look at the computing space requirement, which is the time is very similar. Okay, the time is look very similar, but the space reduced a lot because we are guessing, and you might hit the goal from the first branch. Then you have a very small computational space because you don't list out everything, right? So there is an advantage. But although it sounds advantage, but you might actually go down to a lot of unnecessary layer because you might able to reach the goal in like 3 layers, but instead you select a wrong one, then you might go down 10 steps and so on. So it might actually not helping you. If your solution able to be solved in smaller layer size, right? But we don't know because like it is a search problem, so we don't know whether you need a width, a wide search or a deep search. You're not sure. So that's why we have a lot of algorithm and we have a lot of criteria to do the selection. And this is the algorithm that we put in robot in order to do the decision making. Okay, next. Right, so we want to put just now that concept, the search, back to our navigation, right? So we want to do in our navigation. So the first thing is we need to discretize. So over here, for example, we have the scenario in upper right-hand side. So we have the robots, we have the obstacle, then within the X, Y, what the robot's supposed to move around. So we try to discretize it into a C space. We call it a C space. So you will get something like the one below. Okay, so this is very easy to understand because you might don't look any different because the axis is the same, the X and Y, and the below the C space, the axis is X and Y. But in other cases, the axis might change, also, which means you have dimension change, and that is harder to visualize when you have dimension change. But over here, we have the dimension similar, so it's easier to understand. So now let us go back to the first slide. So David, go back to the first slide. Right. So now you understand the concept of Hanoi Tower, you understand the concept of search and state space. So now we come back to this, and now you have the idea. So now I try to put you back into the perspective. So from the first step, the green box, you have 8 options. So which is you go down 1 layer on the tree, you have 8 possible. Then in each of the 8 possible things, you have another lower layer that you have some other options, right? And then you can see there are many figures, small figures in the boxes, right? So that figure is actually represent the cost in order for you to determine which next step to choose, right? And that cost can be calculated based on, for example, A star. So A star is like when you want to select the next step out of this 8, you can actually calculate the distance from the next box to your goal point. The distance. So the distance is the cost. So you put down all the distance, then you select the smaller distance, and then you proceed, right? So that is A star. Okay, so you can write this into algorithm to repeat your calculation. Eventually, you will find one path that can reach your goal. So that is how it works. So I hope by now you understand how this path planning and so on. But remind you again, what I explained to you is general concept. It not represent the actual operation in our programming and coding later. Okay, because ROS navigation package and Gmapping and AMCL, they might use a different path planning algorithm that is different from here. But I select a simple one to explain to you the concept. Okay, but the idea, the overall concept of motion planning is the same. Okay, so now you understand this thing. So let's look at the practical one. So then we go to the following slide. Okay, so we want to put this into practice. Of course, if it's not possible to ask you to like start writing the algorithm and write everything, it's not possible. But this course is more important, like to explain you to understand the concept and to focus on implementation. So you are given with this task. So now let's imagine you already can do audiometry, you can do localization, you can do mapping, and you already have the planner. Okay, everything done. So all you need is the higher level decision making. Okay, so the decision making is like where the robot should go instead of how the robot go from point A to point B. Right. So you are going to decide where the robot should go, point A, point B, or point C, and that is your development. Okay. So let me show you what are the tools that you have. So over here, just now we introduced the G-mapping. Now we have the Monte Carlo localization with the AMCL. So if you want to know more, you can go to the wiki page to read more about Monte Carlo localization. It's very interesting to read, but maybe not so easy to understand. But it depends on the background. I think like for Wikipedia, I mean, everyone can have a read and you might able to understand, right, eventually. And a lot of things and interesting things for you to learn. Then you can head to the ROS wiki to understand this AMCL ROS package, okay, if you want to know more. Then the last link will show you explanation about how this whole operation, so what commands that you need to use to run this AMCL package and so on. But I'm going to invite again David to show you the actual implementation. Right, so David, I'll pass to you.
Okay. Now we will use the map we have site before, and we will show you how the robot navigation in the simulation environment. I need to close all the terminal before we use. Okay. The first thing is we also need to start the environment. ROS launch. Gazebo. Jupyter robot. And the second, we need to tell the Gazebo, tell the AMCL node where the map is. ROS launch, turtle, boat, Gazebo, AMCL, and map file, home, Musta, Cat King, WS, maps. And the file name is Moonstar Office. Please pay attention. This is the name of the YAML, not the PGM. And we need, uh-oh. I think I typed the wrong name of the map. Let me check. Map file. Map file. Home Moonstar. 我是帮我看见哪错了 YAML Moonstar Office 没有啊开 King WS Moonstar Let me try again Oh, fail to open image fail to open image Oh, okay I made a mistake because Moonstar Office YAML I copied from the another folder, so I needed to change the name of a folder of the YAML maps. This is a mistake about the position of the PGM. Is it right? Okay. Save. Okay. Transfer. Hmm? Check. Gazebo is email launch map file. Home, most can maps, most office, yeah. Most 10 out waiting for transform from please. Before running coast map. Map does target frame map. Okay, we will start the Gazebo again. And restart the 是 YML 吧，是吧 ？Home star Okay, it worked. All DOM received. That means the node is running. Correct. And the last one is Arvis. So if you have problem, just restart and run again. Most of the problem will be solved. Not Gazebo. Arvis, view, navigation. They also need to make some change about the display of this RVS window. Make it smaller so we can see both the RVS result and the Gazebo environment. I will wrote the RVS almost the same as we see in the Gazebo. Okay, almost here. I can also rotate. If you want to rotate in the Gazebo, we need to use shift and left button to rotate the environment. And the view, we can large and small the view of the environment. And this is the Gazebo, and this is the Arvis. So the first thing is we need to use 2D pose estimate to tell the robot where it is as 2D pose estimate. But the position is not very correct, just almost correct is okay. For example, here, you can see the right green, lots of green arrows. The green arrows means the robot think maybe it will be, it might be. And after the robot moved around in the environment, the green arrows will close to the robot. And I choose the 2D knife go, means the go position. So the robot, I will show you. The robot will move along the path it planned. So I will change the method of display to make the video flow. And this is a go position, and I choose. And I choose another one. The robot will plan a path according to the obstacle and the walls. The green and the right line shows the path. Okay, now I will show you the real and the no, not real. I mean show you the Gazebo environment and the RVs. So I can publish another one. Okay, 2D go here. And if I put a obstacle here, the robot will find there is an obstacle and it will change to another way. Okay, it cannot turn left here. He found the obstacle. And he find another way from the top to move to the destination point. This is the path planning for the robot. Okay, and if you want to move this, remove this, you just need to select them and select it and delete it. And we can also use Python method to set the position of the point where the robot should go. And the first thing is we need to get the position of the point, and we use the publish point. First, I nav the robot back to here, and I click here. But remember, don't click the button on the map. We just move the arrow to get the position. You can find at the bottom of this, we can find the position update according to my movement of the arrow. For example, I choose here. Yeah. Negative 0，帮我记一下这个数，负的0.298，负的2.83是吧？ I open the Python file here. At RC home annual learn rows, RC home annual navigation, and scripts navigation. Never mind, I'm going to we use navigation py, and scroll to a little lower, and we find location A. We change the number here. 0.多少？ 负的。And then we save. Minimize size. Now I run another terminal. Rules run. Okay, here. If you have two monitors, it will be much better. Rules run. Navigation. Pay attention to the information shown in the terminal. The first is click the 2D pose estimate button. It also needed to tell the robot maybe where is it. Okay, 2D pose estimate. Okay, here. And then we can find it shows the get the start navigation test. It get the lines, path here, and move to the goal point. Is point A. After it get the position, it will tell you the robot reached the point A and ready to go back. It will find its way to going back to home. Okay, almost the same way. Okay, this is the simulation environment. Now I will show the real environment. Okay, let me stop the stop the program. Stop the. I will show you the environment. Use a USB camera, so you can see. You can see according to the environment, it's almost the same what you see in the simulation environment. I will use another software to connect with my robots.嗯，为啥看那台屏没有开了吗？好，开这个，开这个，开这个，开这个。Okay. This is a team viewer, team viewer software to connect with the real robot. And I will start the robot. You can, I suggest you enlarge the video window to almost the same as a desktop video, desktop window. And rows, sorry. This is a real robot bring up bring up command. Huh? Sorry. 我看不到那个视频窗口，我只能从你那看。So the robot is at the bottom of the wall, near the bottom of the wall, and second is almost the same command, but this is a real robot. The bot. Try navigation. Oh, okay, navigation. Demo. Launch and the map file. I will check. Sorry. Huh? The file is at almost the same folder here. Most office. Okay. Yeah. 没错。哎，这个是那个输入法开了那个快捷切换。老敲错。我下条写了。So we almost get the same result outcome received. Okay. And the Arvis. View navigation .py. Okay. Let's start. Okay. The first is we also need to route the route. Okay. 我现在是不是视觉优先的那个？ Now you can see the robot is not at the right position. So we need to tell the robot where is it, maybe where is it, here. The arrow shows the direction of the robot, okay. We use a 3D sensor to get the map and navigate the robot in the environment. And then I click the destination result, destination point. You will find the robot move to the destination point, almost the same in the simulation environment, almost the same. So that means if you program in the simulation environment, you can copy the file, the program to the real robot to get the almost the same result. And I'll show you another way. You get the new way to the destination result point. 你去挡，你等会儿，等我告诉你了。你去挡这个位置，你去挡这个位置，你别动，现在别挡。我给他一个这个位置，你去挡这个位置。啊。Now I will get the robot back to the start point, but I will send Mr. Max to serve as a obstacle to the robot. You can see the Max blocks the way for the robot. The robot will start get the path here, but he finds that is an obstacle to block the path. So the robot make a new way here, maybe a long way to the destination. So if the obstacle move to this way, the robot will stop here because he will never go back to watch again. So this is a 2D nav go. And I will also show you the publish point method, use the navigation.py file. And I choose maybe point here. 3, okay, 3, okay, I got the point. And I will also find the, where is the, 这是啥? Navigation, 能看清吗? Scripts, navigation here. Okay, 我把这个调过来。换一个，change the position. Oh, I can use this position. I can use this position almost as I select on the map. Okay, save, close, and run a new terminal. Rows run, and RC home, navigation .py. Okay, please pay attention to the display in this terminal. Uh-oh, wrong position. I just need to move. So the first is to also we need to estimate the position of the robot a little right. Okay, let's see what happened. We got the path to the destination point. Okay, can get this path. After the robot moved to the destination point A, it will show you, the robot will tell you it got here. It's arrived here, reached the point, and go back to the going back home. And the Max will also block the way path. Let's see what will be happened. He get the, maybe he find the new way. He need to make some decision. Okay, it's moved, and find the block. We can also find some information in this Windows. The robot shows the method, the ACML node tells the robot it maybe cannot get the way, so it cleaning the course map and maybe it will make another way. Maybe they need time to think about the how to find the way. 那边有个障碍，可能他认为 road cover behavior state. If the robot didn't know where to go, it will route. And we can see if you get the new plan, maybe, okay, it's moved. So not block the robot, sorry. Okay, that's all. Thank you, Jeffrey.
Right, thanks, David. I think like just now the problem is the robot actually scans something in front of the TV. So on the RVs, you can see like it actually have one obstacle over there which is not appear. So maybe just now like when Max passed through and the robot scanned and got that obstacle over there. So I guess that, but yeah, well, the robot's still able to find the escape in order to go back to the origin, right? Which is good. Okay, so thanks David and Max for the demonstration, and I hope everyone now can see that your development in simulation in Gazebo, even the map we scan in Gazebo model, can be used in the real world as well, as long as we have these two model which is matched to each other. And thankful to Jupyter Robot that you can download the Gazebo model, the environment model, from the link that we provided. And then you can actually do your development, and eventually we can test on the in the real environment. Okay, so I think that is a very nice thing that everyone can try to develop for autonomous navigation. Right, so let's go back to the slides. Okay, so all the commands and everything you can refer to the slide, and all the operation you can refer back to the video after this. So we will upload the video later on our YouTube channel, and also we'll post it on our website, so you can refer, and you can refer the command and also the instruction based on the slides and also the PDF file that you can download. Okay, so now let me explain about the assignment for today. So as a practice, today the assignment is very straightforward. So basically what you need to do is very similar like what David and Max have just demonstrated to you. But you need to add in something. So first, you need to add in the speech interaction. So now you can see, just now you can see like all operation is done either on RVs, on GUI, on click, mouse click, or we actually run the code on terminal. But we want it to make it, how to say, more interactive. So you can use our speech module that you learned 2 weeks back, how to actually give the instruction to the robot based on speech. So you can use the speech recognition to recognize the keyword. For example, just now we write all the location A, the figure. So from the RVs, you can actually get more waypoints. So waypoints is the important point that you want to make the robot understand certain instruction. For example, if you ask the robot to go to kitchen, exactly where you want the robot to go. So you need to specify, you need to define first. So once we have done the map, usually we will pick several key points. Okay, but over here we call it the waypoint. So you can pick, like, for example, in the middle of the kitchen, in the middle of the living room, in the middle of the bedroom, and so on. And also we can put like in front of the door, in front of the cabinet, in front of the table, because those are the point that you want the robot to go in order to interact with the user. So you can collect all these points, and then you can, based on the RVs, based on the map, you can get all the coordinate, and you can specify, you can write down all these things in your code. Okay, you can create the database, you can put it on the code, then you can specify, like, for example, location A belongs to kitchen. Then you link kitchen to location A, which is location A, you already type in location A, X is equals to something, Y is equal to something. So if you use the speech, you tell the robot, go to kitchen, and then in your code, you have linked like kitchen belongs to location A and location A belongs to this coordinate. Then you can send this coordinate to this navigation package, and the robot able to say, yes, I'm now going to the kitchen. Then the robot will move to the kitchen and wait for the further instruction there. So that is the assignment, the application that you can do based on all the tools that we have developed and provide you as an example. So all you need to do is just to assemble all the example code and do the tuning by yourself, right? The algorithm, the logic. Like in the navigation.py, the logic is like go to move to location A and then it come back to the home. But maybe you don't want that. You want like move to location A based on what you say and then keep on listening. If you give another instruction, then you go to point B and point C and so on. So as a practice, I would recommend you to do at least 3 waypoints in order for you to understand how to write this algorithm. And this example, I tell you, will be very, very useful for your preparation for the competition. Okay, so I hope you understand this and you can add this. And next week, we will talk about the integration, we'll talk about the preparation of the competition. So which means we'll integrate, for example, speech, navigation today, and how to combine this with your visions part last week. Then you can have a lot of application you can develop. Then you try to imagine what scenario, for example, a scenario in a hospital to assist the patient, or a scenario at home to assist the elderly, or to take care of the children, or in library and so on. Then you put into this scenario, you put all these modules together, you create the application, and that will be the task for your competition. All right, so I guess I have explained almost everything for today. So let me go to the last slide. Last slide. Okay, so just at the end, okay, I just want to show you briefly. David, maybe you can off the sound. You just play the video from 7 minutes. You can off the audio. Okay, so I just want to share this as a closing for today's lecture. So it is actually a TED Talk by Chris, which is the manager, Google manager for this autonomous driving project, which is before the Waymo. Okay, so so this talk he mentioned about how Google actually developed and what are the insights. Okay, so over here I just want to take one small part to show you a comparison. Okay, over here you can see exactly what happened in Google Car, autonomous car, and you can.
So it can be much safer than a driver assistance system can ever be. That's enough about the differences between the two. Let's spend some time talking about how the car sees the world. So this is our vehicle. It starts by understanding where it is in the world by taking a map and its sensor data and aligning it to. And then we layer on top of that what it sees in the moment. And so here, all the purple boxes you can see are other vehicles on the road.
Okay, thank you. Right, so let me explain while you're running this video. Right, so you can see similarly, we in autonomous car, we use the mapping, we need to do the map, and then you have the laser rangefinder to scan the surrounding, but now it's no longer 2D, you have the 3D, then we have the obstacle, you can see it start to mark out all the obstacles, then you have the line, you can see that line is actually like path planning. So these are all very similar to what you have done or what you have seen in this class. So although it might not be exactly the same, but the underlayer concept and everything is very similar. So you can see. So what I just want to point out is like you can actually link this thing and a lot of applications. So for mobile robots, but of course the port from whatever that we have here to the actual scenario, it might need a lot more work, but the basic concept and everything is very similar. So I just want to show, especially for example, if you look at this, you can see the laser scan in order to get the obstacle. So this, the color and everything, the distance, very similar like what you see in others, right? Okay, so I just want to show you that the tools that are provided by ROS and the example given is very professional. I mean, ROS is a very professional software that you can actually leverage this for very nice research work and so on. So hopefully, like you can make full use of the example that's given to you, and also the tools, all these open source tools, and hopefully like you can use it for more application, especially for service robot. Okay, and for indoor navigation and outdoor navigation, although the basic concept sounds very similar, but it have a lot of technical difference. Okay, so the in terms of the accuracy, the speeds, and so on are quite different, right? So for example, like over here, it tried to recognize people, and last week we talked about people detections and so on. So you try to put all those things together, and eventually what you learn in this class is actually the very, very fundamental basic, but this basic point you to the direction that eventually you can come up with a very practical application. Okay, so I'm done. Yeah, I'm about 6 minutes over the actual time. So I'll close the session. And yeah, David, you can stop the video. Thanks. Right, so we'll go back to the slide, the last one. So again, so if you haven't signed up for the competition, please sign up. You haven't write down the attendance list, please write down the attendance list. And if you haven't give the feedback form, please write us the feedback form, right? So that we can plan more. And if you have any question, you're welcome to ask us. I can spend some time over here. You can ask in the group chat, and we can tell you. And especially David and Max is over here, so they can show you the actual robots. And if you have any things that you want to know about the actual robots and so on, you can ask now, since everyone is around. So if you have nothing more, David, you have anything to add?
Nothing. Thank you, Professor.
Okay. Right, so thank you very much, and thanks for the big turnout today. So it's quite surprising that like over 30 people actually attended this session. So I would like to say thanks for your joining, and I hope to see you again next week. And please also spread this thing and ask your colleague, your student, your peer, and everyone to attend our session next week as well. And next week we'll talk more about the integration, so how to put all this thing together. And then we will use the competition as the scenario to show you how to build practical application for service robot. Right, thank you everyone, and I will see you next week.
Thank you, see you.
Thank you.